You roll up to an open pit mine, ready to 3D scan last month's excavation. Jumping out, you set up your drone, attach your LiDAR sensor, and start capturing the data. Just as you're wrapping up, the site supervisor asks if you can map a series of tunnels. They want to scan and remote inspection before sending anyone inside. Luckily for you, your drone is equipped with one of the world's best UAV LiDAR autonomous navigation systems. 30 minutes later, data in hand, you're back on the road. Next up, a 5-kilometer stretch of roadway for corridor mapping. You quickly mount your LiDAR sensor to the vehicle, and within minutes, you're scanning the entire route without leaving your vehicle. At the end of this corridor, there's a parking garage that's in scope and needs a full interior and exterior 3D scan. No problem. First, you drive the exterior of the building, then off comes the sensor from the vehicle mount and onto your backpack it goes. You cover the building's major spaces, then switch to handheld scanning for those tight nooks and crannies. As you're heading home, you get an urgent call from the office. A client needs a rush scan of some sewer pipes. Impossible to enter on foot, and there's no way the drone will fit in there, but time to bring out the remotely operated crawler. A single LiDAR system handling all of this sounds like a pipe dream? Nope, it's Emesent Hovermap ST-X. The year is 2006. A young man by the name of Stefan Hrabar has just completed a PhD in robotics and autonomous systems at the University of Southern California with a specialization in drone autonomy, and is headed to Australia to join a team focusing on UAV autonomy with the Commonwealth Scientific and Industrial Research Organisation, an Australian national research laboratory that's on the cutting edge of SLAM algorithm development and autonomous navigation. And as LiDAR sensors shrunk in size and weight and the cargo capacity of drones increased, there was a crossover point during those early years that Stefan was there where they were able to start mounting LiDAR sensors on drones. At first, the primary intent of this was to aid in autonomous navigation. While Stefan was tackling the aerial side of things, another group at CSIRO was using LiDAR to aid in the navigation of ground-based robots that were working in GNSS-denied areas, which drove the need for positioning and localization in such environments. This led to the implementation of using LiDAR with SLAM. You see, at the time, we already had mobile or kinematic LiDAR acquisition, but that relies heavily on GNSS measurements for trajectory correction and cannot really be used reliably in GNSS-denied areas. Their solution was to take a LiDAR sensor and rotate it 360 degrees to get a full panorama field of view and integrate that with the SLAM algorithms they were developing. And remember, at this point, the LiDAR measurements were being used for positioning and localization, not for mapping. At some point, the dots connected and they realized there was real value in the maps that were being created as a byproduct of the autonomous navigation. Stefan's colleagues at CSIRO, the team that was focusing on ground-based navigation, took their SLAM algorithm to various survey equipment OEMs throughout the industry and basically said, we got this thing called SLAM, you can use it to do mobile mapping. Is anyone interested in commercializing this? Unfortunately, they were mostly met with skepticism and doubt until they spoke to Graham Hunter of 3D laser mapping in 2012. After some back and forth, GeoSLAM was founded as a commercial co-venture of CSIRO and 3D laser mapping and went on to bring the very first SLAM scanner to market, the ZEB1. You could say they pioneered the commercial SLAM scanning market, a market that's worth $670 million today. While all this was going on, Stefan and his colleague Farid Kendul and the rest of the aerial group at CSIRO were working on a second-generation SLAM algorithm that could operate in real time and had a level of flexibility that an aerial solution demanded, so they rebuilt the codebase from scratch to meet their requirements. And in 2018, Emesent was founded and the Hovermap was launched, no pun intended. Ever since, they've been iterating and improving upon that SLAM algorithm and the hardware that uses it to refine one of the most versatile SLAM scanners ever made. And GeoSLAM was eventually acquired by FARO in September of 2022, but their proprietary SLAM algorithm continued to live on in FARO's new SLAM products. Emesent's latest creation, the Hovermap ST-X, uses a single Hesai XT32 LiDAR sensor, a significant upgrade from what the Hovermap ST used, a 16-channel Velodyne sensor. This gave the ST-X better accuracy, better range, and double the points per second. Now, we've covered the specs of the XT32 quite a bit in the VLX3 episode, and these are far from the only two manufacturers that use this specific LiDAR sensor. In fact, it's probably the most common LiDAR sensor used in SLAM scanners across the industry, because it's also one of the best LiDAR sensors for this application. It's cost efficient, has great specs, and is readily available. Over 500,000 Hesai XT32s were sold in 2024 alone. Now, the vast majority of those were for autonomous navigation solutions because, after all, this is Hesai's primary target market and what this puck was originally designed for. It just so happens to check a lot of the boxes that a SLAM scanner designed for mapping needs. Now, I have to asterisk my praise of the XT32 a bit. When comparing it to other LiDAR pucks that were made for obstacle detection to aid in autonomous navigation, it's great. But when we compare it to purpose-built mapping LiDAR sensors like those used in Regal's VZ600i or ZNF's FlexScan, it's really not that close. If you've ever seen the raw data of an XT32, you know exactly what I'm talking about. It takes a lot of filtering to get a product like the ones we're used to seeing coming from the ST-X or VLX. And you can only filter so much before the assumptions that filtering takes start to affect the integrity of the data. We'll dive into this more in just a minute. Emesent chose to focus on a lightweight solution with modularity in their product because while it would be nice to have dual LiDAR sensors or 4 1-inch cameras built into it like the VLX has, or a beefy IMU and extremely accurate LiDAR sensor like the FlexScan has, neither of those solutions can be attached to a drone for aerial capture. And this is the Hovermap after all. As such, concessions had to be made to achieve Emesent's main purpose, which is not only mapping, but also aerial autonomous navigation. They designed the Hovermap with a dovetail system that allows it to be swapped into a variety of platforms very quickly. You can slide a handle on it and clip a battery onto your belt for handheld use, which is great for quick deployment in small areas. You can slide it onto a backpack, either with a GNSS antenna for trajectory correction or not, for hands-free use. You can slide it onto a FreeFly Astro Max or DJI drone for aerial capture, or fix it to a suction cup mount that can attach to almost any vehicle for corridor mapping. It's basically the Swiss Army knife of laser scanning. From what I've seen, the SLAM algorithm from Emesent combined with the trajectory correction from GNSS allows the Hovermap to avoid SLAM breaks in many of the environments that other SLAM scanners would tend to struggle in. When I run a VLX, I have to be quite cognizant of my surroundings in the geometric diversity I have available to me. If I push it, I'll get a SLAM break, and that could lead to having to recapture that entire dataset. It appears the Hovermap is more resilient to such issues, and theoretically, it makes sense based on the science behind their sensor. Some of the datasets I've seen where I was told it captured data just fine were quite impressive. That being said, I did not directly test this aspect, and without proven data to back it up, I can only be so confident about this specific characteristic. For image acquisition and colorization of data, a GoPro Hero Max 360 panorama camera takes video during LiDAR data acquisition, and then frames are pulled from that video clip in Aura, Emesent's processing software. Unfortunately, taking this route means you're not going to have nearly as good imagery compared to what you get from the VLX. Anyone that's tried to pull stills from a video and compare that to pictures taken from the same camera knows there's a significant loss in resolution with this approach as well. The panos are much closer in quality to the FlexScan that takes a similar approach, but unlike the FlexScan that places their camera high above the operator for an unobstructed view, there's a reduction in the field of view of the panorama images from the ST-X because they don't take this same approach. While the Hovermap has some great specs on the hardware front, we also need to be realistic here. If I did some corridor mapping with a $400,000 Leica Pegasus mobile scanner, is it going to look like what I get from the Hovermap with its mobile mount? Of course not. Likewise, if I'm doing some nadir aerial LiDAR capture with a Regal Vux compared to Hovermap on a UAV, there's going to be a difference in data quality. Expectations need to match reality, and you're not going to be able to replace $700,000 worth of scanners with something that costs a fraction of that and get the same results. Now what we're about to look at next, well, the Hovermap very may well be the king of the hill in this respect. Like I alluded to a moment ago, Emesent's focus isn't solely on mapping, such is the case with the vast majority of other SLAM solutions on the market. Autonomous aerial navigation is also extremely important to them, and in that sense, they are one of the market leaders. Some of the examples I've seen of the tunnels the Hovermap can traverse are just nuts. As someone not used to seeing it, the footage had me white-knuckling it in my seat as I watched the drone skimming past hanging steel mesh and making its way through tight passes without any input from the operator. To collect data autonomously, you can not only set waypoints and have the Hovermap make its way from one to the other, all while collecting data and finding an appropriate route while avoiding obstacles, but you can also set a bounding box and it will figure out how to map as much as it can within that box without any input from the drone operator. Sure, the new DJI Matrice 400 has a little LiveVox sensor to aid in obstacle detection, but there is really no comparison on either the hardware or software front to what the Hovermap is capable of. We're talking about true autonomous flight here. I would have absolutely loved to have this setup when I was doing my tree scanning video. Worry-free flight below tree canopies with a rotating LiDAR sensor, trajectory correction from both GNSS and a SLAM algorithm. I imagine it could rip through over 100 acres per day with ease. I met both Aaron Newby and Justin Simpkins on my usual test site way back in the beginning of May to scan the 250,000 square foot 3-floor parking garage that was also captured with a Leica RTC, Regal's VZ600i, ZNF's FlexScan, and Navis's VLX3. All the same rules applied. I had over 120 independent check shots on this site that each team did not know the location of, and 30 plus demarcated control points that were part of a least squares adjusted control network with a ridiculous amount of redundancy that resulted in coordinate standard deviations of a few millimeters at the most. They were free to use as many or as few control points as they wished and scan the site in any manner they saw fit with the knowledge that I would be running my one-dimensional method of accuracy determination on the data and slicing the point cloud to directly compare point cloud fidelity to other datasets. I think it only took Justin under an hour to capture the entire site using the backpack mounted option, and then I did some capture with the handheld version, and we used the drone to pick up some aerial data as well. Part of the reason the data capture was so fast is due to the nature of Emesent's SLAM algorithm, where those small iterative loop closures that we're used to with the VLX are not required nearly as often from what I've been told from Emesent. And of course, there's no stopping to take pictures because the ST-X is recording video instead. There's one thing most handheld SLAM scanners have in common that I don't hear talked about that much. Holding even a few pounds out in front of you like that over long periods of time can wear your arm down surprisingly quick. I'd like to think I'm not a complete desk jockey and I've been known to lift a weight or two in my day, but I guess I'm just a total wimp when it comes to this method of data acquisition, and I can't imagine I'm the only one. So having the backpack option to take arm fatigue out of the equation is a huge positive. If I didn't, I wouldn't be too enthusiastic about scanning 8 hours a day for several days in a row, but with the backpack, it's essentially no different than just walking around. Something I really wasn't a huge fan of is the way Justin had to set control targets. At the time of the data capture back in May, Aura was only able to work with retroreflective targets for control point demarcation. So he had to go around to my traverse hubs and black and white checkerboard targets and either just lay a retroreflective disc on the traverse hub on the ground or use double-sided tape to fix it to the wall and then manually compensate for the thickness of that target in Aura later to get the extracted front of target back to the actual control point that my survey defined the coordinates of. It was just a really clunky way of demarcating scan control in this example. I get why they couldn't take the approach Navis does, where they can physically measure in control points. The hover map is optimized for aerial capture, and you can't exactly land a drone on a control point to physically tie it in. But there really was a gap in Aura's capability by not being able to utilize black and white checkerboard targets. I can set a ton of vinyl checkerboard targets easily and cheaply, but I can't just print off a retroreflective disc for 50 cents a pop. Thankfully, Emesent just released Aura 2.0 the other week where you can now integrate user-selected targets. So black and white checkerboard targets or really anything definable you can pick out of the point cloud can be used. The new tool in Aura allows you to pick your target with great precision by using arrow keys for minute adjustment after clicking the nearest point in the data. And being able to pick anything out of the cloud to use as a control point can actually open up opportunities to add in control after data capture. Let's say some important targets were destroyed and it wasn't noticed during data acquisition. You could pick out the corner of a sign in the point cloud and use your total station to measure that same feature the next day and use that to fill in the gap of the missing control. A couple weeks after data collection, I got the processed point cloud back, which I ran through my QC process that created over 2,000 unique checkshot baselines using the 120 plus discrete checkpoints. If you want more information about how this process works, check out my video on measuring point cloud accuracy. The standard deviations of the residuals ranged from 5 to 8 millimeters depending on the axis, but with max deviations between 21 and 42 millimeters, about 3 times worse than the results I measured from the FlexScanner VLX3. When I shared my findings with Emesent, at first they were somewhat skeptical considering their accuracy report was showing much smaller values. The problem with the way they were measuring accuracy is that unbeknownst to me at the time of capture, only 6 control points were being demarcated with retroreflective targets. And while Aura does do an initial rigid transformation of the point cloud to control to assess accuracy prior to the final non-rigid transformation, which is an awesome feature by the way, this only checks accuracy prior to final processing, and even then, 6 points over 3 floors and 250,000 square feet is not a good sample size. They could have also ran all the way through processing and excluded some of the control points for use as independent checkshots inside of Aura, but were making a bad situation worse by reducing an already tiny amount of control points. And we certainly can't trust the residuals of the control points after a non-rigid adjustment. The trajectory and thus the point cloud transforms and distorts to fit those control points. That's kind of like throwing a dart at a blank dartboard and then painting a bullseye around it after. Not to mention, we're introducing error in the accuracy measurement by relying on the automatic target recognition algorithm combined with the manual manipulation to account for target thickness, an inferior method of accuracy measurement compared to the one-dimensional method in these circumstances. Any way you cut it, they just didn't have the data available to them for a reliable accuracy measurement. We all agreed that these results were suboptimal and most likely caused by not nearly enough control being applied, which meant Justin had to fly all the way back out to Florida, now smack dab in the middle of a triple-digit Florida summer day, to recapture the site, this time using significantly more control points, and the results ended up being about twice as accurate as the first attempt. I measured standard deviations of the residuals ranging between 3 and 5 millimeters, with max deviations between 12 millimeters and 25 millimeters depending on the axis. A huge improvement. Still not quite as good as the VLX or the FlexScan, but for SLAM, it's not that bad at all. And let's talk about these values for a second. It's important to note here that this method of accuracy measurement is using planar features to determine these accuracy values, because typically we are creating planar objects when we digitize man-made structures, and that's usually what SLAM is being used to capture. In just a moment, we'll look at the accuracy of complex geometry by slicing discrete sections and comparing those to the other sensors. Secondly, a lot of us, myself included, get way too hung up on a certain scanner having 3mm accuracy versus 5mm accuracy, when half the time a client has no idea how these numbers are being calculated, what they actually mean, and oftentimes have little idea of what they truly need. Do you really need 3mm accuracy across an 800,000 square foot site? Do you mind explaining why? Can we not separate a local accuracy within the same general area of the dataset versus the accuracy needs from 2 points separated by 500 meters and 20 walls? Once in a blue moon, you'll stumble across a savvy client that knows what they need and, more importantly, how statistics work. But point cloud accuracy is still very much a gray area with no standardization of how it's measured. How many accuracy reports do you see with zero mention of the coordinate quality of the total station points being used as reference? It's still very much a wild west in this regard, and when we layer on the fact that digitizing the data adds a whole other source of error, and oftentimes a very substantial one, it muddies the water even further. All this to say, try not to get too hung up on a few millimeters here and there on the wall or a roof, when what we're about to look at next is probably more important depending on the application of the data. In the first 2 episodes, I sliced sections of each point cloud and compared them to each other and to terrestrial scan data in the same several locations across the test site. I did this to observe how much a particular scanner was or was not able to preserve complex geometry, as it's a well-known issue in the world of SLAM that the fidelity of the point cloud takes a major hit compared to terrestrial scan data. This is caused by several factors that are a result of using a LiDAR sensor not purpose-built for surveying and mapping, such as the Hesai XT32 in this case. This dataset was pretty much exactly as expected considering the LiDAR sensor used. Not that that's necessarily a bad thing as long as you know full well what to expect when using a SLAM scanner. It's just not going to be as accurate, precise, or preserve detail as much as a scanner with a LiDAR sensor built from the ground up for survey. Obviously, there are benefits to using these LiDAR pucks, otherwise almost every SLAM scanner wouldn't be doing it. They're very price efficient, they're lightweight, they're readily available, and until someone starts mass producing a LiDAR sensor specifically for SLAM mapping with a high level of precision and small spot size, this is the nature of the beast. And make no mistake, the XT32 is a solid choice as far as SLAM scanning goes. You're leaps ahead of a 16-channel Velodyne style puck, and there's really no comparison to those little SLAM scanners out there using a Livox Mid 360. Now, the FlexScan would be the exception to this rule. ZNF used a very accurate and very precise LiDAR sensor purpose-built for mapping, but it's not cheap and it's not lightweight. There's always a trade-off. Once I really dove into the cross-sections, it was apparent the ST-X was about the same as the VLX in terms of smoothing out features. In some places it was better, in some places it was worse. Does this really matter though? If a corner is rounded off, big whoop, right? We can just digitize before the corner on the wall and fill at the corners. In that specific example, yeah, sure, you'll probably be okay. But if we need to digitize a small water supply line or electrical conduit, That gets pretty damn tough with a dataset from a traditional SLAM scanner. Just a few weeks back, I scanned a site with a SLAM scanner that uses an XT32 style puck that's a good example of some of the limitations we just talked about. When we look at the door thresholds in the data, it gets really tough to accurately define them. The doorstop is more or less not in the point cloud, and it smoothed the threshold out to a curved surface. This is fine for a rough floor plan, but trying to use this for high detail, high accuracy work, and you're asking for trouble. This same dataset also did some really funky things in smaller rooms. This wall, for example, is a constant thickness in reality. In this corner is a sharp 90 made from cinder block, although you wouldn't know it looking at the point cloud. You just have to be really careful where you use SLAM and know what it's good for and what it's not good for. And of course, some SLAM scanners are better than others. Even though most are using the same hardware, the algorithms are different. Some filter more than others, and that tends to exacerbate these issues. And again, the FlexScan is excluded from pretty much all of this, being it uses entirely different hardware. Processing the data in Aura is very straightforward and quick, but still manages to retain a very high level of customization in terms of the settings of how the data is aligned, filtered, and colorized. And most importantly, it's local, so we're not paying for each dataset we process. We'll look at how the parking garage dataset was processed to give you an idea of what it all looks like. First, we import the raw data, then the control points, and adjust the processing settings to our liking. Right away, you can start to see what I mean by the number of settings we can manipulate. Now, you can run with the default settings as those are the most commonly used, or select one of the presets, but being able to tweak things just so is a huge plus for people such as myself that like to geek out on the nuts and bolts of exactly what's happening to our raw data. While Ivion is great for people that just want to upload their data, adjust one or two settings, and the next day your data is processed, if something goes wrong or you feel like it filtered out too much of the data for a specific use case, there really isn't a whole lot you can do beyond reaching out to Navis's support team and seeing if they can help. Not saying one approach is better than the other, but I personally prefer to have control over how my data is processed, but I also get a lot of people want the set it and forget it style of processing too. And as far as processing time, we're looking at a roughly 1-to-1 ratio compared to capture time if you're not using control. So 60 minutes of field capture takes about 60 minutes of crunch time, and double that if you are using control. After the first processing step has been completed, Aura automatically detects as many retroreflective targets as it could with its automatic target recognition algorithm and does a rigid transformation of the point cloud to those targets and their supplied coordinate values. Like I mentioned previously, I really like how it stops here and lets you check the applied control to find any blunders in the data. And now you can also define any targets that the algorithm missed or manually pick user-defined targets in Aura 2.0 and set certain control points as check shots if you have enough to do so, and those will be removed from the next step, which is a non-rigid adjustment to better fit the data to the surveyed control points. A current limitation of Aura worth mentioning is that you cannot use both trajectory correction from GNSS measurements and external survey control simultaneously. Although the word around the water cooler is that this might change in a future update to Aura, so keep your eyes open for that. Once the second step of processing is finished up that performs the non-rigid adjustment to control, a full resolution and a decimated LAZ of the point cloud are automatically exported along with an accuracy report. You can now view and manually filter the data directly in Aura. During the import process, we did adjust some settings to take care of automatic filtering, but these tools allow you to take a targeted approach at cleaning your data. Next, we'll colorize the data using the 360-degree video clips from the GoPro Hero that we already talked about. After colorization is complete, Aura will create 360-degree panorama images that have a CSV associated with them that hold the position and orientation information of each JPEG. I do wish I was able to export an E57 with the panorama images embedded already, as I can with the VLX or FlexScan. I could imagine trying to walk clients through importing images into their software of choice could be painful, not to mention I'm sure there are some software packages that cannot ingest these images seamlessly. If you captured your project with multiple datasets, you can now go back into Aura, import these processed datasets, and merge them using a non-rigid approach. Aura essentially reruns the SLAM between overlapping datasets and creates new loop closures that did not exist previously. Remember in episode 1 where the VLX datasets failed to align to each other and we saw duplications in surfaces? That was caused in part due to Ivion not taking this same approach. But like I've already mentioned, Navis is catching up on this front with a new tool that I talked about at length in that episode. And a small update on that specific issue, it turns out the field capture was not performed correctly for one of the datasets, and the internal QC from Navis happened to miss it, which actually caused most of the issues in that point cloud. When it comes to pricing, this is where the ST-X has an upper hand on the other two scanners. We're looking at just under $50,000 US for the Hovermap ST-X. If you want the backpack or vehicle mount, you'll need to add another $3,500 each, and obviously the drones are sold separately. To process the data, a 3-year subscription of Aura mapping will run you about $22,000, or you can get a perpetual license with 3 years of support for $37,000. So realistically, you're looking at about $90,000 and some change for the hardware, accessories, and lifetime processing software. That's about $50,000 less than the FlexScan, but you're also getting a terrestrial scanner with a FlexScan. And it's kind of hard to make a direct comparison to the VLX due to the pay-to-play processing approach they take. For just the VLX3, you're sitting at around the $90,000 mark, but as we looked at in episode 2, the cost to process can add up pretty quickly if you're using your scanner a lot. Over the lifetime of these scanners, the VLX is definitely going to cost you the most of the three when you include processing costs. So we're back to the 6-figure question. Which SLAM scanner should you buy? Now, I sidestepped this question last episode, but now that we're wrapping up the trilogy, it's only fair I give a somewhat direct answer to this. And of course, this choice is going to entirely depend on what your use case is. If it was me and I wanted the most accurate SLAM scanner that preserves detail the most, isn't limiting me in the kinds of jobs I can do because of SLAM smoothing, and I get the benefit of getting a terrestrial scanner with it, I'd pick the FlexScan. With my current SLAM scanner, I'm really limited to what jobs I can use it for because of how much detail it loses. If I wanted top-of-the-line imagery and colorization with great point coverage thanks to dual sensors and cloud processing was attractive to me, I'd pick the VLX3. It's comfortable to wear, it creates a dense full point cloud, the processing is quick and easy, the customer support is fantastic as are the learning resources, but it's primarily used in indoor scanning for floor plans, as-built, and high detail 3D models. To say the loss in resolution of the point cloud caused by the LiDAR sensor choice isn't something that needs to be considered would be negligent on my part. It is a fairly large factor when considering what this scanner is meant for. If cost was a big factor to me and I wanted a ridiculous level of versatility, I'd pick the ST-X. You don't just get a backpack SLAM scanner, you get the handheld version for tight spaces and quick deployment, you get a mobile scanner for road corridor mapping, you get a scanner that can mount to a drone for aerial LiDAR, and you get something no other scanner I've tested can do: airborne autonomous navigation. Now it too uses the XT32, but Emesent's target market doesn't appear to perfectly overlap with Navis's. Is it used indoors? Absolutely. Is that the primary use? I don't think so. I see their customers doing a lot of outdoor mapping: streets, mines, stockpiles, topos, etc. Situations where a loss in detail makes much less of a difference. Being able to pull up to site with everything you need in a little backpack and start collecting RTK-enabled georeference data in just a few minutes is something neither of the other two can do. As much as I wish there was, there isn't a single scanner that does it all. There's going to be concessions, and you have to take the cons with the pros. And I don't think I could have asked for more variety than what I got in these 3 episodes. 3 very unique and capable scanners that each fill their own niche. If I came across overly critical in any of these scanners, I want to clear the air and say that was 100% intentional. There are more than enough people online talking about how great every scanning system is without mentioning the drawbacks at all. And unfortunately, I've seen firsthand how this can lead to a small surveying firm making a poor buying decision and losing a lot of money buying a product that they thought would meet their needs only to realize their costly mistake after it was too late. When I make these videos, I do my best to highlight both sides of the coin so people can make an informed decision based on an unbiased review, because we're not talking about a small purchase here. The wrong decision can leave a company in a financial hole that can be difficult to climb back out of. And when it comes to these 3 companies, they all agreed to these videos knowing full well what I intended to do, to find the flaws and highlight them to their prospective clients. Each of them was so confident in their product, they were willing to participate, which, let me tell you, is not that common in this industry. I'd like to take a moment and formally thank Navis, Emesent, and ZNF for agreeing to these reviews. Well, that wraps up the first trilogy of SLAM Wars. I'd like to say this will be the first and last SLAM Wars because I'm very excited to refocus my attention on some educational-based content, and these style of videos take a tremendous amount of time and effort to make, but I would be lying if I said I actually believe that. I'm sure when the next generation of SLAM scanners hit the market, you'll find me back here for a reboot. Until then, thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.